Hello students, um, let's start our today's lecture. It's about machine learning. Um, the outline for today's lecture is we will discuss some basic algorithms of machine learning like k-nearest neighbors, linear regression and k-means. Then we'll discuss some training issues which probably discussed in the next lecture that would include measuring model quality, overfitting and cross-validation. Machine learning is machine learning can be of two types. One is called supervised and another one is called unsupervised. In supervised, we are given an input samples x and the output samples y, and there is a function which maps the input samples to the output samples, y is equal to f of x, and we would like to learn this function f and then evaluate it on a new data. So we assume that we have some data set, a training data set it's called, where we have access to the input samples x and the corresponding labels or output samples y. And then once we train our model, once we learn the function f, we then evaluate it on new data where we have the samples, input samples x, but we don't have y, so we want to predict y for those new samples. Supervised learning, there are two types: classification, where y is discrete, and they are basically class labels, and a regression where y is continuous, for example, a linear regression. Then on the other side, we have unsupervised learning, where we only have access to the samples of the data x, and there are no labels, but we compute a function f such that y is equal to fx is a simpler model. But for training, we don't have y. And if we use if y is discrete, for example, if you want to, if each sample is corresponded to a discrete number or discrete value, then the problem is called clustering. And if y is continuous, then there are multiple examples such as matrix factorization, Kalman filtering, and unsupervised neural networks. Okay, let's see some examples, some real life examples of supervised and unsupervised learning. An example could be if you are given an image and to find out if the image contains the picture of a cat or a dog or a car or a house. And another example could be how a user score a restaurant. For example, if somebody is reviewing a restaurant, he or she would probably give it 1 star or 2 stars or 5 stars depending on his or her experience. Another example is to find out whether an email is a spam or a normal or a ham email. And then unsupervised. In the unsupervised, we cluster some handwritten digit data into, let's say, 10 classes. So then we can assume that each handwritten digit is one of the numbers from 0 to 9. Or another example could be finding out the top 20 topics in Twitter right now, or finding and cluster students based on their CGPA. Like if you have a data set and you want to cluster them, you want to categorize them into multiple groups or categories, but without using any labels, just based on how the data samples are. If, for example, if two samples are similar enough, they would be put together in one category or one group. If they are distinct, then they would be put into two different groups. Let's discuss some techniques. In supervised learning, there is k-nearest neighbors, then we have linear regression, naive Bayes, logistic regression, support vector machines, and random forests. Some of them are used for classification, some of them are used for regression, and some of the techniques or methods are equally applicable to both classification and regression. For example, you can use support vector machines for classification, where the label or the output are discrete, and there you could also use support vector machines for regressions as well. For the unsupervised learning, we have clustering, and there are a various number of clustering algorithms. Then we have factor analysis, topic models, and so on. Let's start with k-nearest neighbors, the most basic machine learning algorithm, supervised machine learning algorithm for classification, where we are given a query item and we find the closest matches in a labeled data set. The good thing about k-nearest neighbor is that there is no model, there is no training. The data set itself is a model, so we can directly use our labeled input data set to find out the label of an unlabeled input by just checking its closest neighbors in terms of similarity. So, for example, if it's one nearest neighbor, then we would just look at the closest neighbor of our query item, and if it matches with that, we would assign the label of that matched item to our query item. If k is more than 1, then we can look for the k nearest neighbors, and then we can return the most frequent label. For example, let's say k is equal to 5, then we would check the labels of 5 nearest items and assign the label to our query item, which is the most frequent one. So let's say 4 of them says cat and one of them says dog or another animal, then we would assign cat to it. So here are some examples. Okay, the issues with KNN is the data itself is the model, so there is no training needed, and the accuracy is mostly dependent upon the size of the data. So if we use more data or more neighbors, then the accuracy improves. The matching is simple and fast because it's just a single pass. And it usually need data in memory, but can be run off disk. But we would need access to a large amount of data at all times, which can be a big issue. But it requires minimal configuration. The only configuration that we need is usually a parameter k, which is how many number of neighbors we are going to use. And two other choices are also important. Weighting of neighbors. So for example, instead of providing equal chance of voting to each neighbor, we can assign a weight to the neighbor based on their distance from the query item. So a nearest among the nearest neighbors, the most nearest would have more weightage in that. So for example, you can use the inverse of the distance as the weight of the neighbor. Another important choice is similarity metric. How do we decide if two entities are similar? So that's also needed. For example, if it's numeric data, we can if it's let's say vectors of consist of numeric values, we can use Euclidean distance for similarity metric. Some similarity metrics are Euclidean distance. It's simplest, it's fast to compute. Then we can use cosine distance, which is good for documents and images. Then we have Jacquard distance, which is used for set data. So it basically depends on how many items in two sets are the same and how many items are different. And for string data, we use Hamming distance. Some other similarity metrics are Manhattan distance, which is coordinate-wise distance. Then we have edit distance, which is again used for strings. It's specifically used in genetic data. Then we have Mahalanobis distance, which is normalized by the sample covariance matrix, and that's why it's unaffected by coordinate transformations. Then we have another technique which is used for continuous data, where we have the output is a continuous number. In linear regression, we want to find the best line so that there is a linear function y is equal to f of x to explain the data. So the data may not be intrinsically linear, but we want to find a close, as close as possible, an approximately linear function which could explain the actual f. The linear regression, the predicted value of y is given by this formula. As you can see here, there is a bias term beta naught, and there are coefficients assigned to each value or to each feature of the input, and this linear relationship would give us a prediction of y. We can actually combine these coefficient terms in a coefficient vector beta, and that would be basically our regression model. And if we use x not equal to 1, then this formula would become a matrix product. So that is y, which is equal to vector x times the vector beta. And we can write all the input samples in a single matrix X, where each row is one sample. So it's a row matrix which is a one sample, and each column consists of a specific feature values for all the samples. And column wise the rows are basically distinct observations, and columns of X are input features. So so how do we know if our estimated function is as good as possible? For that, we would use residual sum of squares, and it would help us to determine the best parameters model for the model, which is actually beta. So this is a very simple formula for n number of samples. For each sample, you calculate add the actual label and find the difference between the actual label and the predicted label, which is beta xi square, and then sum it. Symbolically, you can also use it as a matrix product, and to get the best values for beta, we actually need to minimize this residual sum of squares. So that for each model for each prediction on average, the error is minimized. So it's an optimization problem. You can use a gradient technique. You can calculate the gradient of this residual sum of squares function, equate it to 0, and then rearrange it to find the best estimate for beta. The problem with this technique is the calculation of these matrices, because X transpose X cannot necessarily be invertible. So if the X transpose X is not invertible, we won't be able to solve the linear regression problem using this optimization technique. So for that, we can use iterative regression solutions, because the exact method requires us to invert a matrix X transpose X, whose size is n features times n features. So if it's actually square, the size is square of the features. So for large features, this would be too big, and inverting large matrices is usually a very challenging problem in terms of computation. So even if the matrix X transpose X is invertible, still it would be computationally hard, and in many cases the matrix X transpose X would not be even invertible. So for that, there are many gradient based methods which reduces the RSS error by taking the derivative with respect to beta. So which was basically, which we already seen, you take the gradient and equate it to 0. For it, an iterative solution could be a stochastic gradient, which is an important set of iterative algorithms. Uh, can be this is used, can be as simple as used for linear regression, but as advanced as in neural networks, especially in the deep learning problems. In the stochastic gradient, we use a small subset of the data, input data, which is also called a mini batch, and use it to compute a gradient which is then added to the model. So you'd start with an initial estimate of beta, and then change it by a small amount, which is equal to alpha times the gradient. So if the gradient is if the gradient is large, this would be so that means our initial estimate was wrong, and it would be changed towards making the gradient smaller. Ideally, we want the gradient to be 0. This S alpha parameter is also very important, which is called the learning rate, and this is actually the step size through which at each iteration the beta or the coefficient is going to change. These updates happen many times in one pass over the data set, and one pass over the complete data set is usually called an epoch. So usually we need more than one epoch, but sometimes when there is a large data set available and the data set is of high quality, you can compute a very good quality model by just very few passes, and sometimes even less than one pass. So sometimes even it's possible that, let's say, you have hundred thousands of samples and you can just get the best model by training on a subset of all those samples. Okay, R square values and P values, we can always fit a linear model to any data set, but how do we know if there is a linear relationship? So if there is a real linear relationship, then we can improve the model quality by using stochastic gradient and using many passes, but in most cases we won't have any real linear relationship. Then there could be many options of a linear model which could be used to approximate that non-linear relationship to a linear relationship. And how do we know that if our selected model is the best one? So for that we can use R square values and P values. So you can see in these examples, some of them are good fits to the data, some of them are not enough good fits. So the approach is to use a hypothesis test, as we have seen in our previous lectures, where the null hypothesis would be that there is no linear relationship or beta equal to 0. Then to apply that hypothesis test, we can use, there are various options for hypothesis tests. We can use some statistic, which would be some value which should be small under the null hypothesis and large if the alternate hypothesis is true. And remember again, if the null hypothesis is true, then we do not need to use linear regression at all, because it won't work anyway. So for statistics, we need a measure which is usually small under the null hypothesis. So R squared is a good measure for that, which is basically given by this formula. And as you can see here in this term, in the numerator you have the squared errors, the sum of squared errors, or RSS, but in the denominator you have the variance of the data, the training data itself, so which is basically the squared error of the labels from with respect to the mean. And this term is basically if the null hypothesis is true, this would be a small number. If the null hypothesis is false and alternate hypothesis is true, this would be a large number. You can also describe this as the fraction of total variance which is not explained by the model. As you can see here as an example, the blue dots are our actual data. The red line is our model, a regression model. The green line is the mean value of the data, and so you can calculate this R squared term for this whole data set. If this numerator here is small, then it means it's a good fit, which means most of the data points are explained by the model. And if it's large, then it's not a good fit. Okay, so from R squared we can derive another statistic. The problem with R squared is that it's not a standard value, it's not a standard number. So we want to convert it to a standard number. So let's say we want to convert it to a number which is usually between 0 and 1. So, but R squared values, as you can see from here, it can even be negative, or it can be a very large number. So it can be converted to another statistic which is called F statistic and follows an F distribution. Then from the CDF of it's a standard distribution and it has a CDF, so you can derive the p-value for the data. So for a specific F statistic for your data, you can check from the CDF the corresponding p-value, and that p-value would actually help you to determine whether the null hypothesis is true or not. So for example, if p-value is small, say less than 0.05, we can conclude that there is a linear relationship. Okay, moving on, now we will discuss some unsupervised learning. So we start with clustering. Clustering has one or more goals. It can be used to segment a large set of cases into small subsets that can be treated similarly. This type of problem is called segmentation. Clustering can also be used to generate a more compact description of a data set, let's say a summary, which is called compression. So you can use clustering to compress an image, let's say, while still all the information is intact. Or clustering can also be used to model an underlying process that generates the data as a mixture of different localized processes. And this type of clustering problem is called representation. We'll discuss each of them one by one. Let's see some examples. The example of segmentation could be image segmentation. Compression normally uses cluster-based KNN. For example, it can be used for handwritten digit recognition. And the third type of problem, which was identifying the underlying process, let's say accents of people, because place of origin strongly influences the accents we have. So you can group the people into different clusters based on their accents. The stereotypical clustering is basically where we have points which are samples and they are plotted in a feature space. Let's say there are 10,000 dimensional space for 100 by 100 image. So each value in this given image actually tells you about the values of different pixels. So for example, the highest value 1 is the most brightest pixel, and the smallest value 0 is the most or the lightest pixel, and so on. So okay, then we have model based clustering. So as you can see here, we have clustered data set into 2 or more groups depending on how you look at it. Clustering for segmentation. Here you can see an example. At the input we have we have an image data where we plotted all the pixel values in a 200 by 200 scatter plot, and then at the output of the clustering we have segmented the image into 4 different clusters. So all the pixel values in one cluster can be assigned, let's say, a simple label or one simple value. Condensation and compression can also be achieved through clustering. Then, okay, cluster bias is a problem with the clustering. It's an issue. As a human beings, we conceptualize the world through categories which are represented as exemplars. For example, all the animals that look like this are called dogs, even if they have strong dissimilarities even between them. So we tend to see cluster structure whether it is there or not. In reality, in our actual real life, the data is mostly continuous. So it works well for dogs, but it doesn't necessarily work for other things. So this clustering or exemplifying our environment creates a bias. Okay. We can see an example of Netflix, which is more of a continuum than discrete clusters. So let's say Netflix, instead of assigning or categorizing movies just by genre, it uses factor models, and where KNN can do much better than discrete cluster models. So 2 movies can be considered similar even if they are from a different genre, or 2 movies can be considered different even if they belong to the same genre, based on what the content inside the movies are. Okay, some more discussion on cluster bias. We use clustering more than it should be, because we, as human beings, we assume that an underlying domain has discrete classes in it. This is especially true for characteristics of people. So as humans, we usually tend to put people in different categories on different personality types, where the personality type or the qualities of people could be a continuous number or a continuous value. So just as with Netflix, continuous model can be used, where we can use dimension reduction or KNN, and they would perform better in real life. Okay, some terminology regarding clustering. Hierarchical clusterings, where clusters form a hierarchy, and they can be computed bottom up or top down. So for example, if we are using a top down approach, then at the beginning all the data that we have could be considered as in the form of one cluster. Then you can keep on converting the data into different groups, going down, like let's say you can convert them first into 2 clusters, then further convert it into 4 clusters and 8 and so on. And that would be a top-down approach. If you are using bottom-up approach, then in the beginning, you can consider each sample or each value, each point as an individual cluster, and merge them as you go up the ladder, up the tree. Then we have flat clustering, where there is no intercluster structure. Hard clusterings, where items are assigned to a unique cluster. So in hard clustering, a sample can only be part of one unique cluster. But on the other hand, we can have soft clustering, where cluster membership is a real valued function, and it is distributed over several clusters. So one unique sample can be part of different clusters at the same time, with different values of associations. So let's say we can say that a certain person is half Asian, half British, and so on. Okay, the most basic technique used for clustering is called k-means, and the standard k-means algorithm is based on Euclidean distance. If you change the distance metric to some other metric, then let's say instead of means we can calculate median or midoids, then the same algorithm would be called k-mean or k-midoid and so on. And the cluster quality measure is an intercluster measure only in k-means, and it's equivalent to the sum of item to centroid kernels. The centroid kernel is basically the mean of each cluster. So a cluster would be of good quality if the sum um, of of all items to their centroid kernel is a small number. A simple greedy algorithm usually locally optimize this measure, and this is called Lloyd's algorithm, which is basically finding the closest cluster center for each item and assign it to that cluster, and then recompute the cluster centroid as the mean of items for the newly assigned items in the cluster. So it basically works like this. You can start with the for a given data set, you can start with random some random samples for your initial estimate of the cluster centroids, then assign all the remaining samples to the corresponding centroids based on their distances, and then update the centroids as the mean of the actual clusters. Cluster centers can be picked by sampling the input data. So let's say we choose these 5 points as our cluster centers or centroids, and then we can assign all the points to their to these centers by calculating the distance from these centroids. Then you can update the centroids, which are these cross points now, and then keep doing this process again and again. The iteration could be done either for a fixed number. So let's say we can choose a fixed number, so let's say 10, and we use this process 10 times, or you can do it until there is no change in assignments. So until if you recalculate the centroids and they are the same as the previous centroids, then the algorithm would be stopped. Or you can also fix the number of iterations to the change in quality. So for example, if further iterations does not change the quality of the clusters, then the algorithm can be stopped. K-means is a greedy algorithm with a random setup, and the solution is not optimal because it's locally optimal, not globally, and it varies significantly with different initial points. So if the choosing initial centroids is very crucial for k-means. K-means is a very simple and it has a very simple convergence proof. The performance is of nk per iteration, which is not bad and can be even improved heuristically. Here n is the total number of samples in the dataset and k is the number of clusters. There are many generalization available for k-means clustering. For example, fixed size clusters, or simple generalization to m-best soft clustering. K-means as a local clustering method works well for data condensation and compression. A very crucial parameter of the k-means clustering is the value k. So because we don't have a distinct we do not have distinct labels or groups, so we how many groups do we need the data to be divided into is very crucial in this case. So we can choose k by using some criteria. A KEGG information criteria is widely used for that, which is basically a function of the likelihood, which could be the residual sum of squares, which could be used as quality of the cluster, and QK, which is measure of the model complexity. So we want K to be such that the quality of the cluster is as high as possible, but still the K value is not very large. So that's why AIC favors more compact and fewer clusters. For sparse data, the AIC will incorporate the number of non-zeros in the cluster, which means the lower is better. Okay, here let's see this summary again. There are three basic algorithms that we discussed today: KNN, linear regression, and K-means. Next, we will discuss the training issues. For example, how do we measure a model quality, and then some issues with the models and training, which are overfitting and cross-validation. So that's all for now, and stay tuned for our next lecture. Thank you very much.